All right, today we're going to dive into a really cool field called system identification. Now, you can think of it as being a detective, but for engineers and scientists. It's a way to figure out the secret rules of how something works, even when you literally can't see inside of it.
And that's really the big question, isn't it? Imagine you've got this complex machine, or maybe it's a biological process, or even the stock market. You can poke it with some inputs, and you can measure what comes out. But what's happening on the inside? Its guts are a total mystery. It's a black box. So how on earth do you write an equation, a set of rules that can predict what that box is going to do next?
And that right there, that is what's known as the black box problem. And trust me, this isn't some niche abstract challenge. It pops up everywhere, from engineering to medicine, and it's the whole reason a field like system identification even exists.
At its heart, the concept is actually pretty simple. You have an input, that's something you do, something you can control, and you have an output. That's what you see, what you can measure. All the complicated, mysterious stuff happens in that space between the two. Our goal is to figure out the connection without ever having to rip the box open.
Okay, that's a bit abstract, so let's ground this with a great example. A solar heated house. In this case, our black box is the entire heating system. We have two inputs we can measure or control: how strong the sun is shining and how fast the water pump is running. The big mystery we want to solve, the output, is what's the temperature going to be in that heat storage unit?
So, how in the world do we crack this code? Well, that's where system identification comes in. It is the toolkit. It's our special decoder ring that lets us build a mathematical bridge that connects those inputs to that output.
And just so you know, the ideas we're exploring today are the real deal. They come straight from this foundational book on the subject by Lennart Ljung. Now, it's a really deep field, but don't worry. We're just going to focus on the core process, which is incredibly powerful.
You know, I love this quote from the book because it really gets to the heart of it. This isn't just some clever engineering trick. What he's saying is that this process of turning raw data into an actual model you can understand, that's what science is. It's about creating knowledge from observation.
So let's put a nice, clean definition on the table. System identification is the science of building mathematical models of dynamic systems. And all that means is a system that changes over time. We basically use the data we see to teach a formula how to act just like the real thing.
Okay, so how do we actually do this? It's not magic. There's a clear blueprint, a recipe that we can follow. Let's walk through it. And here it is. This loop is the engine of the whole process. First, you collect your data. Then you choose a basic structure for your model. After that, you find the best numbers to plug into that structure. And finally, and this is so important, you validate it. You test it to see if it actually works. So let's try this with our solar house.
All right, step one, got to get the data. For our solar house, that means we get our computer set up, and for a couple of days, every 10 minutes, we record the solar intensity, the pump speed, and of course, the temperature in the storage unit. This data is the raw material for everything that comes next.
Next up, step 2, we choose a model structure. I love that phrase. It basically means we're picking a template for our equation. We have to start with a hypothesis, a guess about how the system might behave. We might say, hey, maybe the temperature in 10 minutes depends on the temperature right now, plus how hard the sun is shining. That's our starting point.
Now for step 3, find the best parameters. Those are just the specific numbers that will make our equation template work. And how do we find them? We use brilliant techniques like the least squares method. Think of it as a super smart process that tweaks all the knobs on our model until its predictions get as close as mathematically possible to what really happened in our data. It's all about making the error tiny.
And this is where the magic happens. Once we've gone through that process, we've done something amazing. We've turned a bunch of messy, real-world numbers into a clean, powerful, predictive tool.
Just look at this transformation. You start with this jumble of noisy, complex data points, and you end up with an elegant mathematical formula. But here's the kicker. This model is so much more than just a summary of the past. It's like we've captured the system's DNA, the essential rules of how it operates. That's what lets us predict a future. But wait, how do we know the model's any good? How do we know we didn't just get lucky? Well, that brings us to the most crucial step of all, validation. This is the final exam. We take some data we held back, data the model has never, ever seen before, and we say, okay, smarty pants, predict what happens here. If it gets it right, we've got a winner. If not, it's back to the drawing board.
So, why does all this matter? What's the big deal? Because once you have a model that you can actually trust, you can do some truly incredible things. And this technique isn't just for solar houses. It's used to model our entire world.
Seriously, the applications are mind-blowing. Economists use it to try and predict market behavior. Aerospace engineers use it to build the autopilots that fly jets. Doctors use it to model how a new drug might affect the human body. Every single one of these fields relies on decoding its own unique black box.
So in the end, this is about so much more than just fitting a curve to some data points. System identification is a disciplined, powerful scientific method for going from just looking at something to truly understanding how it works.
And that leaves us with a pretty inspiring thought, doesn't it? We are surrounded by complex systems, by black boxes whose inner workings are a total mystery. Now that we know there's a blueprint for decoding them, the only real question is, what's the next black box we should try to understand?